My name is Daniele, and I'm a PhD student at KU Leuven. This is a joint work with Professor Nigel Smart and Younes Taleby-Alaoui. This presentation is about secure fast evaluation of iterative methods with applications to secure PageRank. To begin with, let's imagine we have a system of bank accounts and transactions, and you want to detect fraudulent transactions. So the idea is that you start collecting the data about these transactions over a period of time, and from this history, you form a graph. You do some graph analysis, and which helps you locate suspicious accounts. One way for doing that is the PageRank algorithm, which in this case is used to measure the reputation of single bank accounts. This is motivated by the heuristic observation that transaction networks behave like a web of trust. So individuals are likely to establish relations with those they trust. So this means that the higher is the reputation or the connection of a single bank account, the less likely it is fraudulent. On the other hand, fraudulent accounts look like singularities in this network. So mathematically, you can think a transaction network as a directed graph where vertices are the accounts and the arrows are the transactions. So you can form the adjacency matrix, and by dividing each entry by the odd degrees, you get this stochastic matrix P, whose eigenvalues can be ordered by in decreasing order according to their size. So you have the largest eigenvalue lambda1 equal to 1, then the second largest eigenvalue, and so on. Then there is the event that at any point the money will simply jump to any other bank account with uniform probability. And this is modeled by introducing this public damping factor, lambda, which is typically chosen to be equal to 0.75. The eigenvalues of this matrix, which is still row stochastic, are related by those of P by this damping factor. So this matrix really encodes all the information about this transaction network, which is a Markov process. So computing the PageRank of this network is really to finding the stationary vector of the process of the chain. So you do this using the power method, and the stationary point is the limit of this sequence. The entries will measure the reputation of single bank accounts, and you're gonna investigate those with a low value. So this is easy when you have only one bank, because you have full control of the whole graph. But things start getting challenging when different banks appear and own a portion of the accounts. This is because each bank is only aware of the transactions happening among their clients. So in this example, the green bank can only see this part of the matrix, while the rest is blank. It's secret. And so the banks really need to collaborate in order to detect malign activities. But the problem is, how can they do that while preserving the privacy of their clients? And the answer comes from privacy-oriented cryptographic techniques like HGM or multi-party computation. So a paper from 2019 proposed a solution based on homomorphic encryption, but had some drawbacks like low level of security, and the very design of the scheme didn't allow parties to outsource the computation. They had to stay online, the whole computation. So this work, we propose a protocol entirely based on multi-party computation that aims to solve all these problems. So the idea is, well, we would like to have an ideal uncorrupted functionality F, which as a black box takes the secret inputs of the banks and computes the PageRank of the network and sends the result back to the banks. This is completely safe because this is a black box. And but of course, in reality, this cannot happen. Such an entity does not exist. So we design a multi-party protocol, which implements F and with the security requirements that each party cannot learn anything about the other's input except from what can be inferred from the public parameters and the output of the computation. Fundamental building block here is linear secret sharing. So a secret field element is additively shared. And with this representation, you can compute anything and construct general protocols that achieve active security even when only one party is honest. And most importantly, it allows parties to outsource the computation. So back to our example. Remember that the matrix M has entries which are rational numbers, but this is not a problem because we can encode them as field elements using fixed point arithmetic. So the only thing left is representing the power meter as an arithmetic circuit, which is quite easy. It's just made of multiplications and additions, but the depth depends on the number of iterations. And so the question is, how many iterations do we need? The easy way to avoid this problem is by setting n to be a large number, large enough so that we know we have convergence, which we know happens for 100 or 30 iterations, depending on the application. And well, this is definitely not optimal. So we can do better. We can fix a small error epsilon, and we stop iterating as soon as the difference of two consecutive elements of the sequence is less than epsilon. So this is optimal, but of course it introduces a security problem because we are revealing the number of iterations. Remember that these conditions has to be secret shared. So the question is, can we quantify the amount of leakage due to our revealing the number of iterations? So remember that for the power method, we have the general term looks like this, from which you see that the convergence is dominated by the largest, second largest eigenvalue. So revealing the number of iterations reveals one sample from the geometric distribution that depends on lambda 2. So a paper from the early 2000s says that according to the topology of the graph, we have two cases. Either we have more than two closed irreducible kinetic components, and we are lucky because lambda 2 is exactly equal to the damping factor lambda, which is public. So revealing something that depends on lambda is fine because we don't reveal anything new. Or we have just a single closed irreducible kinetic component for which we can only say that lambda 2 is less than the damping factor. But this is fine because the only way an attacker could exploit this is by collecting many samples from this distribution. And this is not the case in our application because the banks will only perform this computation once. In conclusion, one can formulate a more general question. So if you have a general fixed point problem where the iteration, the condition is secret shared, then is it safe to reveal the number of iterations? It depends on the application you have in mind, actually. Because in the special case where the contraction is given by a matrix, as we saw, this leaks a sample from a distribution that depends on lambda 2. And in the more special case, where the PageRank, where we have the PageRank matrix, then either we reveal a single sample from this distribution that depends on lambda 2, which is a negligible amount of information we leak, or we are in the safe case, in the perfect case, where lambda 2 is exactly equal to the damping factor lambda, and we are not revealing anything new. So this concludes my presentation.
Hello there. So what we're going to be talking about in this talk is we're going to be looking at compilation of programs in secure computing paradigms. So in particular, the two computing paradigms we're going to be looking at is multi-party computation and zero-knowledge proofs. So this is the kind of the basic picture of what we have. So in multi-party computation, we have a bunch of parties there, and they've got inputs, A, B, C, D, and they've got some function they want to compute on their joint input, call this F, and they really want this godlike figure to compute this function for them so that they get the output F, A, B, C, D without revealing A, B, C, D itself. So that's MPC. And in zero knowledge, what we do is that this godlike figure has values A, B, C, D, and what it wants to do is it wants to prove to a third party that there exists some values such that the function equals a given output G. So they're kind of very similar kind of things. Now, because cryptographers don't believe in God, what we try to do is replace the magic godlike figure with a protocol or a procedure. So we've replaced, in this slide, what we've done is just taken the God and replaced it on the MPC side with a bunch of computers connected with a protocol, with a network. And on the zero-knowledge side, we've replaced the God with a computer who is the prover. Okay. Now, traditionally in cryptography, so what we do is we focus on the computers. That's what we do. We're interested in the specific feature. We're interested in the protocol. Okay. That's what we do with traditional cryptography. However, what we're going to do in this talk is we're concentrating on the function. So normally in cryptography, people just ignore this. They kind of go, the function is kind of given to you in some magic way. It's given to you by God. Okay, but actually functions aren't given to you by God, they're given to you by people. So that's what we want to kind of tease apart. So what happens in traditional non-cryptographic compilation? Okay, so what you do is you take some human readable representation of the function, like C++, Java, Rust, and then you compile that into a different representation, like machine code. And this different representation is the representation that the machine takes as input, like ingests as input, and then executes. Okay, so we have human readable format, machine readable format, and then the machine. Now, the machine, building the machine, how you do this, is the focus of computer architecture. The focus of programming language research and compiler writing is taking the high-level viewpoint and turning it into a machine-readable format. So we divide the process into two things, converting from the human-readable format of the function to evaluating the function in a machine-readable format. Now, if we look at cryptographic compilation, what happens is that the machine, the x86 architecture, is the protocol in some sense. So that's the focus of traditional cryptography. It's about how the protocol works. Whereas actually the translation from the higher level viewpoint of the function into a representation which the protocol can ingest, that's ignored. Usually in cryptography, we ignore that. And what we're going to do in this talk is actually look at it and show why this is important and why we need to consider this as a first-class cryptographic object and not just worry about protocols, but also worry about function representations. Okay, so what happens in an ideal cryptographic world? So what happens is, in the ideal world, the theoretical cryptographers live in, they take a function, they represent it as a binary arithmetic circuit, which they can always do because it's like basic first-year computer science. And then they input that binary arithmetic circuit to the protocol, and they build their protocol on the basis that the input to the protocol is a binary or arithmetic circuit. But this is completely impractical in the real world. This is akin to, in normal computing, the computer programmer writing in a restricted form of VHDL. And, no one, except for, really hardcore hardware programmers, no one would do this, okay? So the actual process that happens in the real world is we take the function, we pass it through various optimization processes depending on the protocol we're actually targeting, and then we output a representation of the function which is tailored to that specific protocol. That's what actually happens. But cryptographers completely ignore that process. So this is what we're focusing on. So let's look at what happens when we focus on MPC protocols. So MPC protocols come with various sources, all sorts of bells and whistles that you can add to them. And particularly these are sources of correlated randomness, and secondly, they're special gadgets for special tasks. So when we compile to arithmetical binary circuits, it's they're okay in theory, but it's bad in practice because it doesn't utilize as a first-class object these things that the protocols come equipped with. So a classic example of this is the classic randomness beacon provided by Beaver triples and MPC protocols, okay? So what you do is you take the arithmetic circuit, and then because you've got this Beaver randomness beacon, you can replace the arithmetic multiplications by calls to the Beaver randomness triple. A classic gadget that you might want to consider is when you have linear secret sharing based MPC, you can perform lots of rounds in parallel to avoid rounds of communication. So what we need to understand the compilation process, which takes into account these beacons and gadgets. And in fact, our theory should take into account these beacons and gadgets. So if we take a step back, we've got a function which is operating on sensitive data. And if you're operating on sensitive data, you basically have two key operations, which is declassification, making a sensitive variable non-sensitive, or it's a classification where you take a non-sensitive variable and make it sensitive. So this is classic information flow security, which you would see in Bell-LaPadula models, et cetera, et cetera. So MPC function compilers make strong use of these operations, but which are, again, ignored by the theory community. So a classic example is integer comparison in LSS-based MPC. We perform bit decompositions using Beaver triples bit production, and then we use this using this randomness beacon, and then we open or declassify a masked value, and then we execute the comparison. And this is much, much more efficient, but it makes our MPC protocol become statistically secure. And the reason it's statistically secure is not because the protocol is statistically secure, but the compilation process is statistically secure. So we have to, so this is our first example of where compilation introduces statistical security, or introduces a security concern. But we can also introduce insecure compilations. So consider the following compilation path. We take a function on sensitive input values, okay? Well, okay, we can declassify values. So we declassify X, Y, and Z. We compute f of X, Y, Z in the clear, and we output the result. Now, from a computer compilation point of view, this is a valid compilation. It's functionally correct, but it's not secure because the values are declassified. So here we've got an issue where a compilation methodology gives a security flaw. So clearly we have to understand compilation if we're going to make any meaningful discussion of what security is. So the lesson is compilation affects security, and we need to quantify this loss. So that's basically what this paper does, is we represent a function as a so-called M circuit, which has access, and which is a member of a class of circuits, a class of M circuits, and these class of M circuits are defined by what gadgets and what beacons they have access to. And a compilation process is something which takes a representation in one class of M circuits and changes it to another class of M circuits. And what you want to do is you take an input function, an input representation, which is just the function as a magic gadget, and then you compile it down to a class of M circuits, which is supported by the underlying MPC protocol. That's what we mean by function compilation. So we take it, and when we simplify it, and we want every step of the function compilation must create functionally equivalent. They must be functionally equivalent. You mustn't change the function as you compile. Okay. So what do we mean by security? Because we have two M circuits representing the same function. and we can define their execution trace. You should see the paper for this. And then what we can say is that if this compilation step is perfectly secure, if the traces are perfectly indistinguishable, or they're statistically secure if they're statistically indistinguishable, and it's insecure if the two traces are distinguishable. And all of the examples that we gave, the Beaver triple, randomness beacons, the statistically secure compilation with comparison, the insecure compilation, is exactly this. So this is the definition of what we mean by secure compilation. So that's the first contribution to the paper, is we formally define what it means to do this. So that's basically in the context of MPC, but we could actually do exactly the same compilation process, that so-called zero-knowledge proofs based on MPC in the head, because effectively they're the same. So just do a quick recap of MPC in the head. In MPC in the head, the prover simulates the N MPC parties. The challenger, in an interactive version, challenges the prover to open some of the parties. And then we check consistency of the views of the MPC engines, which are in the prover's head. Correctness comes because of the correctness of the underlying MPC protocol. Soundness essentially requires guessing the verifier's challenge. And zero knowledge is due to the passive security of the underlying MPC protocol. So we can kind of examine it in this kind of three-step process. Okay, so that's kind of basically what happens. And what happens is that in our model of compiling functions, we have this methodology, and it applies both to MPC and to MPC in the head protocols. And we can actually show a concrete MPC in the head protocol using this M circuit representation of functions. So we do this for various different randomness beacons, various different gadgets. We also show how this allows optimization by looking at some very special gadgets. And we show we can reuse all the work on MPC compilation strategies over the last 10 years to build MPC in the head protocol. So this allows us to reuse techniques from the past. So in summary, what would define this compilation protocols? Well, so what should you take away from today? When you define a secure compilation protocol, you shouldn't be using the paradigm of binary arithmetic circuits. That's like 20 years ago. You should be using more modern representation. Function representations are as important as the protocol for security as well as efficiency, and it can be, in fact, more important for performance. If you're building a secure computation system, consider the way functions are going to be used by your system, how they're going to be represented, how are you going to compile the abstract representation that the user uses into the one that the system needs. And if you're looking for topics in secure computation research, there's gazillions, but a lot of them are really, this area of compilation and function representation is very rarely looked at, but it's really where all the effort in practical MPC is. So stop looking at protocols, stop looking at theory, and start looking at compilation. Thank you very much, and I hope you enjoyed the talk.
So hi everybody, we now present a paper, Oblivious TLS via multi-party computation, and this is the result of the collaboration between me, Ivan Demgaard, and Peter Scholl from Aarhus University, and Sven Trefinger from Bosch. Oblivious TLS is a multi-party execution of a TLS endpoint, and in particular, it's a protocol that allows a set of parties consisting in a composite server to securely communicate with any client of the internet. And in particular, the clients don't need to know that multi-party computation is used at the server side. They just need to support TLS. We now introduce what multi-party computation is through a practical example. So suppose that we have a pharmaceutical company and a public health system holding some sensitive data X, for instance, the health data of the patients. And suppose that the pharmaceutical company is carrying out some research and would like to evaluate the function F over the sensitive data X. We can also assume that the function takes as input also secret parameters Y that the company wants to protect from competitors. Clearly, for legal reasons, the public health system is not allowed to disclose X. So the question is it possible to compute f of X and Y, preserving the confidentiality of X and Y? The answer turns out to be yes, it is possible, and multi-party computation is the subfield of cryptography that deals with this kind of problems. One of the main techniques on which this protocol is based on is called secret sharing, and we explain how it works in our example. So the public health system can split X into two chunks, X1 and X2, and we can say that there are some is equal to X. And here the important thing is that none of the two chunks alone is sufficient to retrieve any information about X. We need both of the chunks. So the company can do the same thing with Y, and after that, the public health system can send X1 to the company, keeping X2 secret. And here the process doesn't leak any information because the company needs also X2 to retrieve X. The same is done with Y, and yeah, now we have a secret sharing of the inputs. There are particular protocols that permit to perform computation over secret shared data, obtaining secret shared outputs, and the process doesn't leak any information. And now f of X and Y is just the sum of Z1 and Z2. The public health system can then send Z2 to the company, which can then reconstruct what it wants. Okay, for the moment, we have assumed that the parties have all their inputs, but what if the inputs are supplied by clients? So we have these two parties that perform computation in a distributed way, and there is a continuous exchange of messages between them. We now introduce a new character, this guy holding some personal health data W. And this guy believes in the importance of research, but at the same time, he's a little bit skeptical about the privacy and the confidentiality of its own data. So how can this guy input W into the computation, preserving its privacy? One naive solution is the following. We can use some kind of secret sharing. So we split W into two chunks, W1 and W2, and we send W1 to the company and W2 to the public health system. Now W1 and W2 can be input into the computation, and we can compute f of W. And no information about W is leaked to the parties as long as they don't collude. And here we have to trust them. There is no other way. For instance, we can say that the public health system is not interested in W, and therefore it will follow the protocol. Anyway, there is a problem because the client needs to know how many parties there are, who they are, what type of secret sharing they use, what type of parameters the multi-party computation protocol uses. And yeah, all this information is usually not available. So it compromises the usability of this service. Another issue is that when one of the two parties is malicious, there are security concerns, and that complicates all the situation. Okay, Oblivious TLS tries to solve these problems, and yeah, the idea is that now there is a big mountain between the client and the parties, and the client doesn't know anything about what's going on the other side. We want to use TLS to securely communicate W, but we use it in a special way because now the server is not a user server, it is a composite server. It is made of the union of the two parties. And if on the left-hand side we have a symmetric key K, on the right-hand side the key is secret shared. So none of the two parties know the value of K, they just hold chunks of it. And so the client can encrypt W using the key K, and none of the two parties can retrieve the plaintext because nobody knows K. What they have to do is to use a multi-party protocol that takes as input the ciphertext and the two chunks of the key, and it outputs a secret sharing of the plaintext. Specifically, what we designed is this decrypt black box protocol that takes as input the chunks of the key and the ciphertext, and it outputs a secret sharing of the plaintext. Now the parties can either reconstruct the message if needed, otherwise they can keep it in shared form and they can compute computations over it. If the server has to reply to the client, we can also use this encrypt protocol that we designed that takes as input the chunks of the key and the chunks of the plaintext, and it outputs a public ciphertext that can be sent back to the client. Okay, so the security is based on this secret sharing of the symmetric key, but how can we obtain that? That's not so straightforward. So in TLS, the symmetric keys are obtained using public key cryptography, and in particular, Diffie-Hellman. But if the secret key is known to one of the two parties, that party can reconstruct the symmetric key, and all the security is compromised. So nobody has to know the secret key. We have to secret share it. The parties hold chunks and they know nothing about SK. The public key instead must be public because we have to send it to the client. So we designed this Diffie-Hellman protocol that takes as input the chunks of the secret key and the public key of the client. And this protocol outputs the secret sharing of the symmetric key. And the latter can then be used in during the encryption and decryption. We explain a little bit better what we do here. We use elliptic curve Diffie-Hellman because it's faster and more common. And suppose that B is the base point of the curve, and let Q be its order. Let P be the client's public key. And yeah, as we said, the secret key is secret shared. So SK is the sum of A1 and A2 modulo Q. And here you can understand that no information is linked by the knowledge of just one of the two chunks. The public key is clearly SK times B as usual. So we can try to do the following. So the company set Z1 to A1 times B, and the public health system sets Z2 to A2 times B. And yeah, we can understand that this is kind of what we want, because Z1 plus Z2 over the elliptic curve is exactly SK times B, the point output by Diffie-Hellman. However, there is a little problem, because what we want is a secret sharing of the coordinates of this point. And yeah, it is not so clear how to derive it from a secret sharing of this type. So we have to do something a little bit different. We use these tuples, which are called doubly authenticated point tuples, and they are generated in a preprocessing phase using a technique called cut and choose. Each of them can be used at most once. And yeah, R1 and R2 are random points of the curve. In particular, there are shares of a random point R that is known to the body. X1, Y1, X2, and Y2 are instead elements of the field on which the curve is defined, and they are the shares of the coordinates of R. Okay, how do we proceed? The company sends A1 times P plus R1 to the public health system, which replies with a similar message using A2 and R2. And here no information is leaked about the secret key, because R1 and R2 are random points that mask all the information about A1 and A2. Later on, the parties can sum the 2 points, obtaining SK times B, the output of Diffie-Hellman, plus the random point R that is known to nobody. So this point doesn't leak any information too. Now we have to subtract R in order to retrieve the coordinates of SK times B. And therefore we use this elliptic curve subtraction black box protocol, which uses affine coordinates. It is rather easy to implement it. We just need one division and one square. And this protocol takes as input the coordinates of the public point T1, T2, and the coordinates of R, the shares of the coordinates of R, therefore X1, Y1, X2, and Y2. The protocol performs the subtraction, and in the end, we obtain a secret sharing of the coordinates of SK times P, let it be S. Later on, we can derive the symmetric keys from S, obtaining them in shared form. Okay, regarding performance, as for every multi-party computation protocol, security comes at the cost of efficiency. We did some experiments with 2 parties over a LAN, and the handshake takes around 1 second, whereas the throughput of AES-GCM is around 3 megabytes per second, based on result of other people. And here we only take into account the online phase. We don't consider the pre-processing phase that is needed by the procedure. So to summarize the results, Oblivious TLS is a multi-party execution of a TLS endpoint, and this supports any number of parties. So in our example, we just used 2 parties, but in general, everything is fine with n parties. The protocol can be used at server side, but also at client side, and it is based on a multi-party version of elliptic curve Diffie-Hellman of AES-GCM. And in the paper, we also present a novel MPC-friendly AEAD. And yeah, this is particularly efficient in a multi-party context, but usually it is not supported by the clients. The authentication is instead guaranteed by a threshold eDDSA signature. In order to apply what I presented today, my suggestion is to just consider the potential of multi-party computation and the many interesting applications. And then you can reflect on how applications can benefit from Oblivious TLS. And yeah, that's all. So thank you for your attention.